Welcome back to The Narrow Gap, the learning show that demonstrates in many ways that all you got to do is keep trying and eventually you got it. Whatever it is, you got it. And my performance here, unfortunately, is a piece of that. If you think that I got anything on this show in one take, in one try, you grossly overestimate my ability to talk on camera. So I ask you to love me, jump cuts and all. I have here a letter from a viewer that reads as follows. I'm a student and I really want to learn more about fractions. I really think fractions are cool and lit, and I really hope that you talk about them on a future episode. Nobody would write that. Nobody likes fractions. Meanwhile, teachers have reached out to me and asked me to do a video about fractions because fractions can be an anxiety-driving topic in math for young people. It certainly was when I was your age.
I was your age.
And so, to hopefully spread the emotional damage out, instead of making one humongous video, as I have lately been doing, apologies, I'm actually going to break this topic up into a couple little videos. As I've addressed in other episodes, there is always a level of complexity that hits you when you think you've got a handle on things, and fractions are no exception. When you're young and you start learning about fractions, it is pretty straightforward. I mean, probably you're coloring things, right? Or you're drawing things or circling things on worksheets, and half makes a lot of sense, right? You can kind of picture half, and thirds and fourths and tenths, and you have to identify things from clearly drawn out circles that you can look at. However, after 1 or 2 years of that, you're being asked to compare fractions that have numerators and denominators that are much larger and much more complex. You're being asked to compare the size of things, and it's not easy to do. And your instinct is going to be, I have to draw each fraction. But the instant that the denominator is something insane like 48, it's very hard to draw a wagon wheel accurately so that you can compare it to another fraction that has a denominator of 11. So this first video is going to talk about what fractions are and what equivalent fractions are, and how to compare fractions. I'm not adding, I'm not subtracting, I'm not multiplying, I'm not dividing. I'm just talking about what fractions are. I know there's probably several of you that already know what fractions are, and this will be boring for you. And if it is, I apologize. And there's probably going to be people who aren't as keen on what fractions are, and it'll still be boring for you, and I apologize. But I'm going to dive right in with 3 concepts. That's what I'm limiting myself to. 3 concepts for this video. 1, units. 2, defining numerator and denominator. 3, cosmetic surgery. That seems like a very logical table of contents, I'm sure. So let's just dive right in. So what do I mean by units? Well, I want to talk to you about fractions, and what I'm going to do is I'm going to use a strategy that you used back when you were first learning what numbers were. When you were a little kid and you had to learn your numbers, you started with very concrete examples. So if you had to learn what 4 was, you'd learn it in terms of concrete things, physical things, like these 4 apples that are increasingly genetically modified that I've drawn for you. I'd like to point out that I don't know what this part of the apple is called, but I drew that part for you too. You use a pretty concrete or pictorial example to represent 1, 2, 3, 4. But after a little while, you think about the number 4 as just 4. You don't have to think of it as 4 things. You just say, there's 4. 4 has a certain 4-ness to it. What's 3 plus 1? 4. What's 4 divided by 2? 2. You don't need a picture for it. You just kind of have a sense of what 4 is. When we do fractions, we're going to do much the same thing. When we start learning about fractions, we'll take a number like 3/4 or 3/4, and we'll draw it out. And I'll say, because you know what a circle is, that is 3/4 of a circle. Except that you might have noticed in the last little bit, the coloring pages have stopped showing up. that you're being asked to talk about fractions in a very abstract and weird way, and it might not feel normal. At first, all of your fraction examples have pictures or something physical that you can say that's 3/4 of something. But eventually, with some practice, we're going to try our best to begin to ignore this and just think of 3/4 as a number. It might be tricky to suddenly drop this example or this picture that we, kind of enjoy so much, but I want to eventually get us to a point where we just think about fractions in this lesson as a number, a thing that has a certain 3/4ness to it. One of the ways I intend to be fair in that regard, while we're still using physical examples, is to make sure that all of the examples are 3/4 of the same thing. Meaning, if I'm talking about 3/4 of a pizza or a circle or a pie or something, every pie, every pizza, every circle is going to be the same size. It would be extremely bizarre if I asked you to compare this fraction to 1/2, but 1/2 is this big, right? They'd all be of the same thing. This probably isn't going to be that challenging for most of you. You've probably got a sense of this already. A fraction has a numerator and a denominator, a top number and a bottom number. Okay, looking at it right now, I get why this is somewhat confusing. Let's talk about what each of these things is. Now, the whole value, I'm going to just vanish for a second. It is when we do mixed numbers, there's like a 1 and a half. So the whole value we're going to come back to. We're just going to talk about the numerator and the denominator. The numerator is up here, and the denominator is down here. The top number tends to be received as the star of the show, but it is a number that is meaningless without the denominator. And if you want a physical example, you could take a pizza, and you could cut it into 7 slices. Not 8, not 12, 7. Like a monster. And you cut that pizza into 7 slices. From that point on, anytime I have to describe anything from that pizza box, it is a value over 7. If you have eaten 3 slices out of that box, you, my friend, have eaten 3/7 of a whole pizza. This whole pizza, this specific pizza. So if we were going to describe the denominator in clearer terms, it would basically just be, how is the whole shared? The denominator, in fact, is critical when it comes to comparing two fractions. Here's a fraction, here's a fraction. They both have 2 as a numerator, but they are speaking very different languages with this 10 and this 100 at the denominator positions. If you were to look at this in a bowl of a certain Lucky cereal, 2 out of 100 for marshmallows looks like that, whereas 2 out of 10 looks like that. So how these bowls are shared up vis-a-vis sugary bits and better sugary bits is critical. So I mentioned a few seconds ago that the third topic is going to be cosmetic surgery. And I use that silly way to describe it, cosmetic surgery, because I want us to be able to change what a fraction looks like on paper without changing how much it is. This story takes place at a Costco in winter, and it takes place many years ago when I was younger and hungry for success and also food. I was a substitute teacher at the time, and I chewed my water very slowly to make it last at that point. So I'm leaving Costco in winter, pushing my cart through the snow with probably like a catering bag of rice or a lifetime supply of ramen noodles or something. And I see a cart stuck in the snow in the parking lot. No other cars around it. And I find in the bottom of the cart, where people often forget things like kitty litter or bags of salt, a pizza, a frozen Costco pizza left abandoned, derelict in the bottom of the cart. And it was mine for the taking. I'm not proud of this, but it was one of those humongous, I don't know if they still make them, humongous rectangle pizzas that took advantage of every square centimeter of the pan. So I seized it, I took it home, I cooked it, and I ate it, and I don't feel the least bit bad about telling you about this. Before you judge me, I want to point out two things. One, it was very cold and the pizza was well preserved. And two, at that time, Costco was famous for the amount of salt that they would use to preserve all of these kinds of things. And this pizza was no exception. It was so salty that probably having eaten it, there was less live bacteria in me as a result. Common for the Costco pizza of its day, this pizza was gigantic and split in twain. It had two parts. It had a pepperoni side, and it had one half that was pepper. And just now I see the problem with these abbreviations. Now, free pizza or not, I'm not a wild animal. I did cut the pizza into slices in order to consume it. So let's look at what that entails. I take the pizza, start by cutting it right here. So what fraction did I just make? Or rather, how much of this pizza is pepper? Let's just look at that. How much of this pizza is pepper? Well, there's one pepper piece out of two whole pieces. One half pepper, as advertised. Okay, I'm going to cut it again. How many pieces are pepper now? 2 out of 4. And the goal is I have to cut this fairly every time I cut it so that there's an equal sized piece no matter where you put your finger. Okay, I'm going to cut it again. How much of the pizza is pepper? Well, 1, 2, 3, 4 out of 1, 2, 3, 4, 5, 6, 7, 8. Right? I have to cut it fairly every time. I'm going to cut it a few more times. And if my hand is true, then I could say by counting that I have cut this into 32 completely equal sized pieces, and 16 of them are pepper. All right, so what did I just prove with that whole display? Well, that this fraction that talks about how much pepper there is, and this fraction that talks about how much pepper there is, and this one are all equal to each other. Meaning that this one's equal to this one, and this one's equal to this one, and this one's equal to this one. They're all equal to each other. And any other fraction that I make following a certain rule will be equal to all the other fractions in this type. I've created something of a ridiculous fraction family. Now, even though I kept asking about the pepper side of it, I cut the entire pizza up, including the pepperoni side of it. And this is important. I have to cut everything into fair, I don't know. Those ones are a bit suspicious. But I have to cut the whole pizza into fair shares, even the part that I'm not currently asking about. So I want to look at this series of numbers, and I want to figure out what fair looks like here, because I had to be fair with the knife, right? Cutting all the things up to the same-ish size piece. What does fair look like when we're dealing with numbers? I'm going to pull out these two fractions right here and put them right here and examine them to see if we can figure out what fairness looks like in the world of numbers. So taking away our picture, let's examine this and this. Well, 2 times 8 is 16, and 4 times 8 is 32. Aha! That is an example of fairness. And it also works in reverse. So if you wanted one rule to take out of this, one rule that talks about fairness that you can say is always true when you're dealing with a fraction, whatever you multiply or divide the top by, you must do the same to the bottom. If you do that, you are now a cosmetic surgeon of fractions. You can take your scalpel or you can take your suture and you can change any fraction following this rule and create another fraction that looks different but is worth the same amount. And that is really the goal for this video, is your ability to do that. So to use an example that is absolutely disgusting compared to all the nice thirds and quarters and halves and sixths that you're familiar with, I'm going to say 4 over 7. And I've picked the color brown to write this in, and I think you know why. If I said 4 over 7, can you take this fraction and make any other fraction that is equivalent, that is worth the same amount to 4 over 7, just make it look different? Well, an easy move would be, yeah, I'm just going to multiply this number by something and multiply this number by the same thing, and I'll get two numbers over here, and it'll be worth the same amount as 4 over 7. So let's take a number at random. I'm going to say, I don't know, 3. I'm going to say 4 times 3 equals 12. And then with the fairness rule in mind, I got to multiply the bottom number by 3. We get an equally gross, weird-looking fraction on this side. But we know that because we've treated it fairly, this fraction is absolutely equal to this fraction. That was thrilling. Let's do another one. Using 7 once again, I now have another weird-looking fraction right here. And if I asked you, just make me another fraction that is worth the same amount as this, following the rule of fairness, whatever you do to the top, you've got to do to the bottom, what would you do? Well, I don't know, multiply the top by 2. Okay, or 20, it doesn't matter. As long as you do the same on the top and the bottom, and you get a second fraction, 7 times 2 is 14, 15 times 2 is 30. These two fractions are equal. Okay? So one of the things on your little worksheet that I've generated is the challenge, make literally any equivalent fraction by following this rule. Now I've used multiplying twice. You can use dividing sometimes, but only in certain cases. There are cases like this one where you can divide the top number and the bottom number by something. In this case, they're both even, so it's a pretty good chance that I can divide both in the top and the bottom by 2. 16 divided by 2 is 8. 20 divided by 2 is 10. This works sometimes. And the reason I say sometimes is that fractions are very rational, very stable things, and one of the ways that we make sure that they are stable is we don't put decimal numbers up here. You could divide, for example, both of these numbers by 11, but you'd get two very bizarre decimal numbers on the top and the bottom of this fraction, and it's not really in keeping with the spirit of fractions to put decimal numbers in there. It's not like it's against the law, but in terms of math class, we tend to keep decimals and fractions separate at this point. There are going to be many occasions where teachers ask you to reduce fractions, and this is definitely the area of cosmetic surgery that we were just talking about. So if I have a fraction like, I have to find a way to smallden this as much as possible so that it is using division, another fraction over here that gives you the same value as this, just looks like the smallest possible numbers. And there are lots of ways to reduce. You could probably guess where this is going, but you can do this in steps, and it's totally fair. So if I said, okay, 10 and 30, they're both even. They're both even. So I'm going to divide them by 2. 10 divided by 2 is 5. 30 divided by 2 is 15. I have reduced this fraction. This fraction is smaller than it was before in terms of the numbers that are being used in it. And it is worth the same amount as this first fraction was, although it is not reduced all the way. And when they say reduce in most math classes, they mean as small as possible. So you do a few things. You look for prime numbers, for example. Once you've hit a prime number on either the top or the bottom, it's a pretty good chance that you're either done or almost done. 5 is a prime number, right? You can't divide 5 by anything except 5 and 1. So you're at a point now where you're like, oh, maybe I'm done. But then you take that prime number and go, wait. Can I divide this number by 5 as well? Yes, I can. So divide by 5, divide by 5. Yeah, 1 over 3. But to say this again with a little bit more emphasis, pay attention to prime numbers. Prime numbers are numbers that can only be made through multiplication by multiplying itself and 1. You can't make them any other way. You can't divide them any other way. And the first number of them, the first string of them, are 2, 3, 5, 7, 11, 13. There's no way to divide 13 by anything except 13 or 1 to get a whole number. Same with 5, same with 3, same with 7. I know that 1 gets included quite a bit, but it's really not a prime number, but it kind of belongs, but it doesn't belong. It's the Pluto of prime numbers. Consider it that. It doesn't really fit for your needs here. So 2, 3, 5, 7, 11, 13, they're like magic numbers. So when we're having to reduce a fraction through division, we look for these numbers and other larger ones. But, in your grade, kind of keep your mind on these. And that's going to help you decide whether you've got reducing to do or not. Meaning if somebody says to you, hey, the fraction you end with is 3 over 7, can you reduce that? No. That's a prime number, that's a prime number. There's nothing you can divide 3 by that you can also divide 7 by, except 1. Yeah, time well spent. So these prime numbers, 2, 3, 5, 7, 11, 13, and beyond. So if someone said to you, hey, and I don't know who this someone is that's just walking up to you and posing questions to you, but if it were asked of you, reduce this fraction, I'm picking even numbers again here, but I know that with an even number, you can always at least divide by 2. So I'll divide this side by 2, and I'll divide this side by 2. Okay? You don't have to memorize the entire times table to be able to do this. Just a few rules of divisibility, and a little step at a time, and see what you can do with it. 8 divided by 2, cut in half, 4. 32 divided by 2, 16. Okay. Am I done reducing? I've got a second fraction. It's equal to this fraction. Great. Can I reduce it even more? Well, there's no prime numbers here, and they're both even, so it's a pretty good chance we can do the same trick again. Divide by 2. Divide by 2. 14. 4 divided by 2 is 2. 16 divided by 2 is 8. That fraction and that fraction are equal. Okay. 2 is a prime number. So that should light up your eyes for a second. Go, hey, I think I'm either done or close to being done. There's nothing I can divide 2 by except 2 and 1. There's no point in dividing by 1. So I can divide this by 2, but if I can't divide this number by 2, then I'm done. In this case, I can. So 2 divided by 2, and 8 divided by 2, 1 over 4. All right, Pluto, you're back. You're back in the game. Yeah, once you've got a 1 there, you're done. There's nothing else you can do with this number. So here's another fraction we have to reduce. 6 over 27. It would be really great if I could take 27 and just divide it by 6, but you kind of can't. There are some rules for divisibility that allow you to spot when you can divide things by 3. I mean, dividing by 5 is pretty straightforward. The rules of divisibility for 3 and 7 are a little bit more work to remember, but I can make a whole separate video about that. 11's pretty easy to spot. If you got numbers like 22, 33, you can divide by 11. So you've got a fighting chance on some of these. But with this one, we know we can divide this by 2. That's not an even number. We can't divide that by 2. If you know your times tables or are familiar with them slightly, you can divide both by 3. So we'll try that. Divide by 3 and divide by 3. 6 divided by 3 is 2. 27 divided by 3 is 9. Okay? 2 is a prime number. It's on our list. And it means that we are either almost done or done. Here in this example, I have to ask myself, can I divide 9 by 2? Can 9 be divided by 2 and get a whole number? No. So we're done. We have reduced. It is done. There'll be time in the future for us to do adding, subtracting, multiplying, dividing of fractions, etc. But there is one more thing that cosmetic surgery of fractions can get you, ignoring adding, subtracting, multiplying, dividing, everything else, and it is comparing fractions. Which fraction is bigger? 3/4 versus 1/5. Which is bigger? Well, I mean, there's a few ways to solve this. when we start learning about fractions. One is we can draw it, and if they come from equal sized pizzas or circles or whatever, and we draw them out relatively fairly, we can see that there's more of the original circle here than there is here. Another way to talk about it is that if we can imagine 3/4, it's bigger than a half. So using a little bit of a mental math strategy like this, you can say, well, this is bigger. It's bigger than a half than this. Okay. There are other ways to compare them. So I've got two fractions here. And again, we already know the answer, so it's not going to reveal anything to you that's too exciting. But I'm going to make a new fraction right here for this one. And I'm going to make a new fraction for 1/5 right here. They will be equal to their original counterparts, and then we can compare them much more easily. In order to compare these, what would be really helpful is if they had a common denominator. There are times when your teacher is going to ask you for the lowest common denominator. But I don't care about the lowest common denominator. I just want a common denominator, any common denominator. The number on the bottom. If it's the same, then we know that these are cut up into the same amount of pieces, and the top numbers are very easy to compare as a result. So I don't really need to know the lowest common denominator. I just want a common denominator. I want a number that goes in the bottom that can be divided by 5 and 4. And the best way to find that is to multiply 5 and 4. Is there a smaller one? Maybe, I don't know. My brain is not going to do that. I'm just going to take this number, and I'm going to remember them for their partners. I'm going to say, here's 5. Take 4, multiply by 4. And then whatever I do to the bottom, I do to the top. Okay? And I'm going to take 4 and multiply it by 5. And whatever I do to the bottom, I do to the top. 5 multiplied by 4. 5 times 4 is 20. And on this side, if I've done this correctly, 5 times 4, still 20. Great. On this side, I've got 1 times 4. Whatever I do to the bottom, I do the top, and it is 4. And on this side, I have 5 times 3. 5 times 3 is 15. 15 over 20. Okay, let's get rid of some non-essential stuff. Which fraction is bigger? Yeah, there's 15 out of 20 versus 4 out of 20. It's much easier to compare the size of these two fractions when they're speaking the same language and they're both out of 20. I've got two fractions. I want to know which one is larger. I have to compare them, but they're speaking different languages. This one's out of 5, this one's out of 10. They need a common denominator for me to be able to compare the top numbers. There is more than one school of thought on this. Once again, you need a common denominator. You could go for what's the lowest common denominator. Or you could go for just any common denominator. It depends on your preference. If I said, all I care about is a common denominator, I don't care how big it gets, multiply these two numbers. It's fine. It's fine. 5 times 10. 5 times 10 is 50. You're going to wind up with two fractions that are both out of 50. As long as you're being fair, it's not the worst crime in the world. Okay? So 5 times 10 is 50. Whatever I do to the bottom times 10, I got to do to the top. What's 3 times 10? 10 times 5 is 50. Multiply that by 5, multiply this by 5, what do I get? 4 times 5 is 20. Which fraction is bigger? Green. Which fraction is bigger? Green. The other way you can go about this is to look for like a sort of a shortcut, because sometimes you've got two numbers chosen for the denominator that have some common multiples, and you can go, hey, wait a minute. 5 times 2 is 10. I'm only going to change this side and then compare it. So if I'm going to make two fractions out of 10, this one's already 4. 5 times 2 is 10. 3 times 2 is 6. Which fraction is bigger? The green one. Green one, green one, green one. It is totally, in my view, reasonable to do either one of these strategies. If you like finding the ability to make the lowest common denominator, okay, then make the lowest common denominator. If you want to make any common denominator and make it gigantic, as long as you follow the rules, 5 times 10 is 50, therefore 3 times 10 is 30. 10 times 5 is 50, therefore 4 times 5 is 20. I think it's perfectly reasonable to forge ahead doing that. There are probably students who are aware that this can be changed in yet another way, meaning that I want two fractions and they're both out of 5. This specific example allows us to take 3 over 5 and keep it just as it is, and then take 4 over 10 and go, hey, I know a little bit about division. These are both even numbers. We just did reducing. We divide by 2 and divide by 2. And 4 divided by 2 is 2. The larger fraction is the green one. But really, now we've got 3 different strategies all giving us the same answer. The green one is the bigger fraction. So it doesn't really matter which one you like best. It's good to know more than one. It's good to pay attention to some of the patterns of multiplying and dividing. It's going to help you. But any one of these will work in this case, depending on what you can do with these two numbers. It's nice to know that if you just multiply this by this, you can get a common denominator. It might not be small, but it will be common. It'll be shared. I'm going to show you one more example in the world of which fraction is greater, and show you what I mean. Here are two fractions. You really can't multiply 8 by anything to turn it into 6. And you really can't multiply 6 by anything and turn it into an 8. You can multiply them by each other. 6 times 8 is 48 and 48. So if I took the 6 and multiplied the top and the bottom by 6, I get a fraction out of 48. If I took this 8 and multiplied the top and the bottom by 8, I'm going to get a denominator of 48 on this side. And at least in this case, they'll be speaking the same language. And then I just had to compare top numbers once I calculate them. So let's do that really quickly. So 8 times 6 is 48. 3 times 6 is 18. Taking that number and then multiplying the bottom and therefore both of them by 6. Okay, and I got a fraction, denominator 48. That's a little crazy, but they'll both be out of 48 in a second, so really it's not that crazy. Whatever you do to the bottom, you do to the top. So I take this 6 and I'm multiplying it by 8, which I did to get 48. And then I'm multiplying 4 by 8. In this example, the blue fraction is bigger. We just showed it. 32 is bigger than 18. They're both out of 48. They're both speaking the same language, and 32 is bigger than 18. Okay? Even though we have the answer, I'm going to do this question one more different way, and it's a way because 8 and 6 are commonly chosen for this type of question that you might see on an assignment or a test or something. You never know. But I'm going to show you the way that we change both fractions, but not in such a grand fashion as to make them 8 times 6 equals 48. If you were to skip count by 8s, 0 8s, 1 8, 2 8s, 3 8s, and so on and so forth, and you were to skip count by 6s, no 6s, 1 6, 2 6s, 3 6s, 4 6s, you will find that both lists contain 24. And because of that, you could make two fractions using cosmetic surgery with denominators of 24 instead of this gigantic number over here. And some teachers are going to prefer that you do that. I do not, because again, we already have the right answer. I don't know why, but let's just do this for the sake of argument to say, here's one more proof that the blue fraction in this case is bigger. All right, so 8 times 1, 2, 3 is 24. And 3, if you do this to the bottom in the green fraction, you're going to treat it fairly. Cosmetic surgery rules say that I got to multiply the top number by 3. I'm going to multiply the top number by 3. And here I go. 3 times 3 is 9. On this side, we're multiplying by something different. It happens that 6 times 1, 2, 3, 4 is 24. So multiplying the bottom by this, the rules of cosmetic surgery say that I have to multiply the top number by this. Very same thing. And 4 times 4 is 16. Well, we've now created two equivalent fractions. This fraction, this blue fraction, and this blue fraction, and this blue fraction are all worth the same amount as each other. And this green fraction, this green fraction, this green fraction are all worth the same amount. They're just cosmetically adjusted, so they look different. But in this case, we've created two new fractions for one green, one blue, and lo and behold, the blue numerator is bigger. But we kind of knew that was going to be the case, but that is sometimes a strategy that you can use. But I say this because not everyone has got the times tables memorized to such a degree that they can kind of compare and contrast these sorts of lists in their head. If that's not you, your story is not over. You are not defeated. My suggestion, if you are ever uncertain, is to just take the two denominators and multiply them by each other. You're going to have a common denominator, okay? This is going to be useful to you in adding and subtracting fractions too, because we're going to be using some similar skills to find common denominators in those questions as well. So as usual, I created a little worksheet for you to download and use at home, class, whatever. If you're already working on that, plucking away on it like a bingo card while I'm talking, fantastic. If you want to take it and download it right now, there's going to be an answer key below. I hope you join me for my next video, which is going to be about improper fractions and mixed numbers and that sort of thing. I'm really going to go at this a piece at a time. If you want to hit the subscribe button and check out the next one when it arrives, the one thing I can promise you is that I will never overwhelm you with content at the rate that I make these things. But hopefully you'll join me next time for more exciting fraction action. Keep practicing. You've got this.
Just got lightning crack in the background.